Start with this one first. Just recall from yesterday, and I already drew this diagram so you remember. This is what light looks like when it passes through a pane of glass. It gets bent, right? It gets bent toward the normal, slowing down. Then it goes to exit glass, which speeds it up, going back to air, and it bends away from the normal. So inherently, what we end up having is like a staggering of the image. We see the image shifted over a little bit. And that was the example with the person's finger and that big piece of prismatic glass in front of it. So this is the idea from yesterday that we're really focusing on. But just to recall that concept. So let's start first on focusing lights. So we're just focusing any EM wave. And the concept here is to use a lens. And you've used this before. When you were a kid, you used a magnifying glass. That was a lens. In chemistry and biology, we use a microscope. It's a lens. If you have contact lenses or reading glasses or distance glasses on, they're all lenses. It's a matter of how the lens works and a matter of the application of how you want it to work. So for example, a person that is farsighted and a person that is nearsighted would use two totally different lenses with two different applications for two different reasons. One is trying to see further, one is trying to see close. If you get older and you can't see far and you use your short distance vision, whatever, you have to wear bifocals, right? Ben Franklin, the bifocals, the whole top and the bottom, which are now I think called transition lenses. The top is for far and the bottom is for if it's for close, but it's not like a split in the piece of glass. The glass curvature, it's amazing. This is calculus, by the way. It's all calculus that does this. The curvature of the lens changes as it goes from the top to the bottom, which is why the top part of the glasses can be used to see far and the bottom can be seen near. It's not physically two different lenses. It's one lens that is formed in a way that is curved that way. It's actually really kind of cool when you think about it. So the concept here is to refocus light and to change the way light impacts us. So let's talk about two different types of lenses. First, we have a converging lens, which will do what it sounds like it's going to do. It's going to converge the rays. And then we're going to have a diverging lens. A converging lens is convex. Convex. Do you know the difference between convex and concave? Convex and concave? Do you remember the difference? You want to give me an explanation?
Right inside and convex also.
Yeah. So the way I remembered it when I was younger was concave. Think about a cave. If you lived in a cave, literally a cave. A cave, you would hollow out part of like a mountain, right? And that's what a cave is. It's usually an area of rock that has been removed and chiseled out. A cave is literally caved out in a sense. So you think about a cave, the shape of a concave or diverging lens looks like this. Okay? Looks like this. A convex or converging lens simply looks like this. Now, the light rays that are coming from the sun, they impact or affect or they meet the lens, and when they do, they are all moving parallel to one another. Okay, remember from that Cosmos videos, that was one of the things he talked about, how light can be assumed to be moving in parallel waves. So one ray of light is next to the next ray of light, which is next to the next one, etc., etc. The reason we can say this, by the way, is because of the size of the sun. The sun is so massive that all the light rays that are coming to the Earth, by the time they get to us, the only ones that made it here are pretty much going in a straight line. Think about the sun, okay? Visualize this being the sun. Now, over here, visualize the Earth, a speck in space compared to the sun. Anybody do this? No one knows this one? Some of the boys might don't know this one. From that in the middle. I was thinking about this one. So you got the sun over here. For later, I'm saving it. So you've got the sun over here. You've got the Earth over here. The Earth is a dot. Now the sun's rays come out in all directions, but the rays that we get are really the rays only from one part of the sun. So if you think about a little part of the sun, so this is the sun again. These couple rays, they might come out pretty parallel to each other, close to it. The other rays all come off at angles. But because we are so small, we're only getting some of the rays of the sun, and the rays that we get are pretty much coming in parallel to each other. So as a result, when we draw lenses, when we think about light entering a lens, we can assume the rays are parallel for now. When it hits a converging lens, it does exactly what it sounds like. The rays get bent. They get bent. The middle ray does not get bent because it's entering at 90 degrees. Remember that. When something hits a piece of glass, if it hits it at 90 degrees, which is only the middle, right here, this is perpendicular or normal to the surface. When a ray hits a lens normal to the surface, it passes right through. It hits that normal, it passes right through. But look up here now. Look at this angle now. Now, here's my ray. It's hitting the light or the glass at an angle, and that causes it to bend, and it turns. But when it hits at 90, it goes through at 90. And that was something that we talked about with refraction in general, that it has to have an incident angle to have a refracted angle. If the incident angle coming in is perpendicular to the surface, it's not going to bend it at all. Here.
But isn't it like not exactly perpendicular because it's curved?
So the word perpendicular is actually only applicable at an infinitesimally small area. A light ray, a wave, is so small that the part that it's hitting, although it seems like it's still kind of curved at the tip there, it's not. Because if you scale things down really small, a curve is actually an infinite amount of little lines and dots connected. You can think of it as little lines. If I drew a polygon, think about your polygons. What is a circle? Anybody know? Like a circle is defined as a locus of points equidistant from the center. Whatever. What is a circle really? A circle is a polygon with an infinite amount of sides. Think of a polygon. Squares, pentagons, hexagons, octagons, nonagons, decagons. I don't know 11. 12 is dodecagons. Anyway, as you increase the number of sides in the polygon, doesn't each side get a little bit shorter every time? And if you have an infinite amount of sides, each side would be infinitely small, which is really what a circle kind of is. So what I'm trying to explain to you is that at this point, although it looks like it's curved, if I zoomed in enough here to this exact middle location, there's a little point where it's kind of flat. And it may not be physically there, you may never even be able to see it, but that one ray, that middle point is not going to bend the lens. Okay, and the same thing is going to happen for this middle part here, or for the diverging lens as well. So for the converging, just recognize that even when it leaves the lens, it continues to converge. Okay? So this is a converging lens, also known as convex. Convex. Now, by the way, some lenses can be combinations of convex and concave. There's a lot more to optics that I'm going to go over. You're noticing already that I've cut out like certain names. If you went to public high school that covered Regents physics, you had to take the Regents exam at the end of the year. In the Regents exam, the topic of optics and imagery is actually a big topic. It is not on the SAT subject test. And we kind of categorize you guys to take, or push you guys to take the subject test. You don't take the Regents. So I'm going to go into crazy math. It's a lot of math. And it's a lot of trigonometry. Tons of triangles. So with virtual images, the whole concept of how your eye actually inverts images. Did you guys know that? What you actually are seeing right now is the opposite of what you're seeing. It's crazy. Everything you're seeing is inverted. But your brain can take what you're seeing and redo it and actually literally give you a picture of what you're physically seeing. So like, put your hand up. I'm seeing this, right? I'm giving you a high five right now. But my brain is actually interpreting you, but in reality, the eye is seeing your body inverted like this right now. It's kind of crazy to think about. And that's like a virtual image. Certain lenses change an image. And a combination of different lenses can magnify or like make an image look smaller than others. There's a cool example, yeah.
So you said the brain changes the image.
Yeah, there's some. I don't know the neuromechanics or whatever that's involved, but I do know that what you're physically seeing is an inverse of the actual image that's in front of you. I have it's here. My seniors always mess around with this, or they did in engineering, so I'm trying to find it. Oh, here it is. Perfect. All right. So I think a couple of you guys have seen this already during the year, just in the room. Have you seen this? So take a look at this, and I'll pass it around. It looks like a little pig. Okay? You know the marble in there. There's a little pig in here. And if you put the little pig in the middle, stand him up. It doesn't have to really be standing up, who knows. Okay? You look at this from the side. Try to look at it at a bit of an angle. It looks like you might see a pig floating up here. Do you see it?
Oh my lord.
People that are close will see it.
Whoa.
Try to push through the pig. It's not there. But it looks like it's there.
Oh.
Okay, so pass it around. leave the pig in the middle, and look at it from kind of an angle from the side, and try and see that the pig looks like it's floating above, up here. When in reality, it's at the bottom. And this is just a concave surface that is specular. So you're seeing kind of that reflection from it. You might have to get like a little bit of a lower angle. You might have to move the pig around a little bit. It looks like it's above, but it's not actually there. That's what's called a virtual image, literally. How many of you have been testing out VR stuff now, or lately? Or AR, VR, which one is it? VR, AR, artificial, virtual, whatever. Artificial reality, virtual reality. If you have like certain phones now, I think like the new Samsung does it, right? You can actually make it into like a headset. That's physically what you're like seeing. You're seeing virtual images now. Obviously, it's a little bit different because you have this headset on. It's not really in front of you. But the concept of being able to actually touch something that's not there. That's like the beginning, the basics of virtual reality, like the very, very basics of it. I'm not like informed in the area, so I don't have much to give you there. A diverging lens does the opposite, right? It takes these rays. Let's go ahead and draw these rays. And let's let them diverge a little bit. The middle one is straight though. The other ones diverge a little bit more. And then when they exit the diverging lens, they continue to diverge further. Rain.
What if they enter at an angle?
They do enter at an angle, technically.
Oh.
So these are entering at angles, which is what's causing them to bend. So although these light rays are parallel to each other, wherever it intersects the lens besides the center point, it's going to be coming at an angle already. But yes, if it came at another angle, it would distort even more. It would just cause it to bend in that direction.
And hypothetically, if we knew like stuff about the curvature, we would take the angle back.
Sure, absolutely. And when you get glasses, if you know anything about that's pretty cool, right? When you know anything about your glasses, the glasses themselves have an actual magnification ratio and stuff. If you get contact lenses, you can see your prescription. That has to do with how much things need to be changed. And we talked, was it in this class? No, we'll talk about in a second how glasses work and contact lenses work. I want to get to it on the next slide. So I'll hold off for a minute. Okay, but again, converging and diverging lenses. The one on the right is a diverging lens. I'd rather you know those words. Convex and concave are not as important because some lenses are both convex and concave. So it's not as important that you memorize which is which in this one application. Okay? So just understand the concept of converging and diverging. So it's a focal point. A magnifying glass is which of these? Which one's a magnifying glass? Converging, yeah. Magnifying glass is converging. The way you can remember it, besides the fact that the shape of it is convex, how many of you have tried to burn stuff with a magnifying glass before? As a kid, no one has tried? I think I've tried sometime. Go out in the summertime and like burn things, but not ants. That's terrible. Yeah, I remember when we were kids, you used to hold a magnifying glass and you'd hold it on the light would focus a little dot beam of light, which would heat up. And if you did it on like a piece of dry plant or like a dry leaf, the leaf would catch fire. They use magnifying glasses in the summertime when people are camping actually to start a fire during the daytime. If you want to get a good fire started, you have kindling, you would actually use a magnifying glass. You'd use obviously flint for it, but magnifying glass works. But this is what's happening. It's taking the sun's rays and focusing them on one little area, and that area will eventually heat up enough to burn. Okay, and yes, you can burn ants. You can. It's pretty mean. Whatever. So let's take a look at these two examples here. So we're going to talk finally about the applications of these with your eyes. So most of you in the room that are wearing glasses or contact lenses have myopia, which is nearsightedness. And that simply means you can see near. The word nearsighted means you can see nearsighted. You can't see far. Right? I'm nearsighted, for example. So those of us that are nearsighted, what's happening is this. The light rays enter the eye. They go through your lens in your eye. They focus too soon. The light rays should be focusing on the very back of the eye, which is called the retina. The retina is like the aperture. You remember in the video of Cosmos, you talked about aperture, that little hole in the tent, and the one ray of light came through, and that's how films were used to be made. That's the same concept here. If these light rays don't focus properly on the aperture, everything seems out of focus, doesn't it? Everything seems blurry, and that's why people squint. You squint. What are you doing when you're squinting? What are you creating when you're squinting? You're creating two apertures. An aperture is literally a little hole in the camera lens that allows a picture to be taken. And that was what he was talking about in Cosmos. So when you're squinting, that's what you're doing. If you forget your glasses at home and you need to wear glasses one day, don't even squint. Take a sheet of paper, poke a hole in both spots. Hold it up to your eyes all day long. It will work. Believe it, you've tried it before? It will actually work. I'm not joking. It's my science teacher told me when I was a kid. It's true. Poke 2 holes, little holes, and those are your apertures. As long as they're exactly equidistant of the 2 center points of your eye, and you can line them up, it'll actually work as well. I mean, it's not obviously comfortable at all. And the minute you move it away, suddenly everything's going to seem really out of whack. So you probably want to less. But if you forgot that, it would work. Now, because these focus too soon, I don't want to converge them. I want to diverge them a little bit. Think logically about it, right? I mean, it says it right here, but I want these rays to kind of separate for a little so that they'll converge a little bit later. Because right now they're converging quickly. But if I can get them to be out here, then it's going to take a little longer to converge and maybe it'll hit the right spot. So take a look at the rays. They diverge for a tiny bit. And then as soon as they hit the lens, which is right here, they converge again. Your eye's lens is a converging lens, by the way. It absolutely is. So because they diverge and had a wider starting point, they hit at the right location, known as your retina. Okay, and the opposite is true for hyperopia. You don't need to know these phrases, by the way. I'm not going to test you on them at all. You should know nearsighted and farsighted and the concept of what you're doing with the lens. Okay? So here, these rays focus not too soon, but too far away. They focus all the way out here. So I need these rays to converge sooner. That's what I need to have. So what do I use? A converging lens. The converging lens gets the rays to start converging sooner. By the time they hit your lens, look where they are. They're already here and here. Instead of being all the way at the top of the lens and the bottom of the lens and not focusing early enough, now they're kind of a little bit down from the top, a little bit up from the bottom. So these are a little narrower, so it focuses sooner. So they're correcting what's happening to your eye. Your eye is to do with its shape. The shape of your eye is what's telling you which of these you are. Now, I don't know exactly how it works. We talk about, what's it called when your eyes, they're different? When one has one prescription and the other has the other. Astigmatism. Does anyone have astigmatism? You have astigmatism? Oh, wow, enough. Wow, that's incredible. The other class, only one person raised their hand. Does anyone actually know? I don't know much about it. Since the other class, I have not had a chance to look it up. What's the deal with astigmatism? Do you know? Yeah, give me a little feedback.
Too much light enters your eye, so when, for example, if you stay out like a street light at night, it's like a lot of light diverging. It looks like it's like going out at the same time. It's not like one light, it's just like a lot of light being spread out.
So the light coming into your eye is what's the effect, not the shape of your eye.
Well, it deals with the shape of your eye. So
Okay.
that's probably the reason why there's
More or too much light coming in.
yeah.
Okay, so tell me more.
Because, I don't know, for me it's one eye.
Yeah, it's usually one eye. It's usually not both eyes for people.
Yeah, one eye is bigger than the other one, like depending on the shape of the eyeball.
Okay, so the shape definitely affects it, but you're saying it has to do with the amount of light being let in. Very interesting. Anybody know any more about this? About, I almost said glaucoma. Glaucoma is the one with cataracts and stuff in your eyes. Astigmatism. It's definitely the shape of your eye that causes this, so that makes sense that it's the shape also that would adjust it. And do you know why it's usually only one eye? Traditionally, it's only one eye that you have astigmatism in. It's not usually both eyes. Any idea? No? Oh, okay. Just curious. I thought maybe those who had it might know. Anything else I want to mention for this? No. Okay. So a couple applications we just went over. Now, let's get into the kind of tough part of today's lesson. All right, this honestly is the tougher part for today's lesson. So, and this is the fish tank demo I really wanted to show you guys. So I promise I'm going to try and get it in you. Just got to get to the Petco when I can bring this in at some point. But now apparently we're going to use it as a mentor fish afterward. I let the other class convince me to actually get fish. I told them, well, okay, we'll get fish. But then they wanted to put it in the parlor. They wanted to put it in the parlor as a mentor pet. They said every mentor group should have their own, like, you know, you have class pets. So now like a class pet. I don't think so. I got what I said. I was like, guys, it's not middle school, it's high school. We don't have class pets. But they wanted like one for our mentor group. Anyway.
Are you guys getting one or multiple?
I'm getting one fish tank for the lab. And then once we're done, then we'll see what we do with it. If we get some, I promise we'll get one.
Yeah, but don't get three, get two.
Get
Three, and then get four.
Three's coming?
Get piranhas.
Get piranhas?
Get lemon sharks. Lemon sharks, lemon sharks.
Alright, anyway, I bad, focus on. Sorry, I diverged. I diverged. So, I know I do that too much. In my freshman class today, I was going off on a tangent about tangents. It worked out really well. Today I diverged. Anyway, so let's look at this. Let's look. Ready? Imagine please, my Apple Pencil is a laser pointer. I don't have one right now, but imagine this is. And I'm shining a laser pointer from water into air. And this is what the fish tank demo is about. That's why it's a fish tank. It's also a piece of glass. So, you take the laser and shine it toward the surface boundary. If it hits the boundary at 90 degrees, it never bends. That was something we talked about yesterday. If that hasn't gotten in your head yet, write it down. If the light ray ever hits a boundary at 90 degrees, it's never going to bend. Okay? It's always normal, it exits normal. The minute it hits the boundary at an angle, it starts to bend. Now, in this example, we are going from water to air, slow to fast. Write it down in big letters. This is only going to work, everything we're going to learn about the rest of this entire section is only true for EM waves, light, for example, traveling from a slower moving medium. Doppler effect, remember Doppler effect, listen for it. You hear the difference in the pitch? Not only the decibel level, but the pitch went down as it passed us. Anyway, something I talked about this the other day, didn't I? Yes. I always forget which class I talked about something. An ambulance went by the other day and I talked about the Doppler effect. It's sound waves. It's an ambulance traveling and driving with the sound waves in front of it being compressed because the ambulance is catching up to the sound waves. So it seems like the pitch is really high when an ambulance passes you, and when it's coming towards you, and when it leaves you, it's a much lower pitch. It's called the Doppler effect. It's not the same thing as a Doppler weather radar. Same idea, though, actually. Anyhow, so back to this concept. We're going from slower moving media to faster moving media only for this idea. Okay, now, what are we seeing in the diagram? Here's what we're seeing. The light ray bends to a certain amount. As the incident ray angle increases, though, the bending keeps increasing more. So I can draw a bunch of normals in, for example. I can do this. So this is scenario 1 right here. Scenario 2, scenario 3, scenario 4, scenario 5. At each scenario, the normal is in a different location. The textbook in this image only puts one normal line in. But every time there's a light ray hitting a surface, you can call that another normal, another perpendicular. So what I'm going to do is, watch, I'm going to put a bunch of normals in at each one of these segments, where each of these hit the surface boundary. Not the first one, though. Okay? So for each of these, I'm going to put a normal at each of these interaction points. What I want you to focus on is the angle itself. Take a look, just look up please for now. I don't want you to actually be writing anything down so you can physically see what I'm pointing to. So here, take a look at this angle right here. That's the incident angle. Now, in the next example, the incident angle got bigger. In the next one, the incident angle got even bigger. In the last example, the incident angle is the biggest. So we're seeing an example where the incident angle keeps going up. Well, the refracted angle does the same thing. This is the refracted angle for the first one. Give me a dimension for this. I don't care. Give me a number. Degrees. That's reasonable. 30, 40. I'll take either of those. Okay? So 40 sounds good. Then I go to the next one. This looks like 60 degrees. Then the next one, though, what is this angle right here? What's the angle between these two vectors from here to here? What's the angle of refraction? 90 degrees. So what's happened, this is a phenomenon. It's amazing, actually. We don't predict this. It's not really predictable. The concept is that the light bends so much that it never passes into the new material anymore. It bends back into the old material. How many of you have been in an in-ground pool at night with a light on in the pool? Have you ever seen how the pool kind of glows? Like if you look from outside the pool will look like it's glowing blue or glowing green. But the light isn't really bright outside the pool, but when you're in the pool, it's nice and bright. This is what's happening. The light source is right here. I'll draw you a pool. When I was a kid, that was one of the things. My dad was an avid swimmer when he was a kid. So he made sure that we had an in-ground pool when we were kids because he always loved swimming. Okay, it was the one thing he was like big about spending money on. So here's the light source in the pool. Okay, and there's the deep end. I'd say this is the shallow end actually over here, right? So there's the deep end on that end. There's the shallow end. The light source is usually in the deep end. The angle that these light rays hit the water surface at is like this last example. It's such a large incident angle. The source is here. So imagine, follow my hand. Look at this light ray. If it hits like that, that's a huge incident angle. That incident angle causes a refracted angle that is so refracted that it bends the light not only back to the surface, but back into the material. So it looks like this is reflection. It's not. Called total internal reflection, though. Misnomer, I know. It's called total internal reflection. What's happening is phenomenal. But it is actually bending of light. It is actually refraction occurring. Again, total internal reflection. Total internal reflection occurs, right? It occurs when the incident angle is greater than or equal to the critical angle. And we'll talk about the critical angle in a minute. But let's just jot that concept down. That total internal reflection occurs when the incident angle is greater than what we define as the critical angle. Okay? And that is the case. Or equal to. Greater than or equal to. I'm sorry. So here's, again, just to reiterate. Take a look here, please. Incident angle, pretty small. Incident angle getting bigger. This incident angle becomes the critical angle right here. This incident angle is now called the critical angle. This measurement, whatever it is, let's say it's 50 degrees. This angle, or anything more than it, would cause total internal reflection. See how this line, when it hits here, it bends it right along the surface? Well, any angle bigger will not bend it along the surface, but it will bend it back in, and further back in, and further back in, as this angle gets larger and larger. So the idea is that if your incident angle is big enough, the light gets temporarily trapped inside. Trapped, temporarily. It will eventually bounce around enough to make it out. Because if this light ray, right, watch, ready? This light ray bounces, watch, hits the wall, hits the ground, comes up, hits a person maybe, bounces back off, and if it goes out at a small enough angle, it will actually exit the water. So the light isn't trapped forever, which is why if you turn the light off the pool, it's not like it's sitting there glowing forever. The light ring is not bouncing back and forth. I want to clear this up because the other class got confused. The question was posed in the other class, and it was a great question. What would happen, like a diamond does the same thing. A diamond sparkles because it's trapping light. I'll talk about the angles. I'll talk about diamonds later, but I'll talk about the angles of diamonds that work. Somebody asked the question, what if you were to take a red laser gun, like a laser beam, okay, and shine it at a diamond ring, and then turn the laser off? The question was, well, it's going to stay in there forever. And I said, no, it eventually escapes, because I wasn't clear about it. Right now, the angles that are hitting this are causing it to bounce back in. But this ray is not going to just eventually, it's not going to stay inside of the water forever. This ray will eventually bounce around enough at the speed of light, so you're not going to see it happening, right? But it will bounce around quick enough that eventually it will exit the water maybe at a perpendicular angle, and then the water's not going to stop it. Or maybe it'll exit the water at this angle, which is not the critical angle, so it'll exit the water. But any rays that are hitting the water's surface at a big enough angle will bounce back in. But the minute you turn off the light source, these light rays are eventually going to find their way out of the pool. And it won't actually glow forever. It's not like it's going to be stuck inside of the pool, and the pool is always going to be glowing in light. Okay? Who was it? Gus. Gus is the TA for physics. So Gus was in my class today, and we were finishing up the section, and he gave an awesome application of this, and I had no idea it existed. Apparently it's right here. You heard of what's called the low line in New York City? Like there's the high line. You know the high line on the west side now? There's something that's being called the low line. Apparently it's going to be an underground farm. I would say plantation, but it's not the right word. Farm. So the whole underground is going to be all this farmland. Now, what's crazy about it is in the past, to do what's called terrace farming in buildings or underground, you know what you have to do? You have to actually use these high-powered fluorescent lamps and stuff and use a ton of energy, which kind of defeats the purpose of farming in the first place, because the whole concept behind farming is that you're using the sun's energy to grow crops. You don't have to put any fossil fuels into it. You don't have to put any sort of energy into it. It's the sun's light that gives it energy. Photosynthesis, right? What this project is doing is it's taking these focal discs that look like satellites on the roof of whatever this infrastructure is. It is taking these parabolic discs, like a satellite disc, that cause the light rays to focus like a magnifying glass when you burn the ant. It focuses those light rays, which then travel through a fiber optic tube, which we'll talk about in a minute. And fiber optic tubes carry light signals. They don't allow light to escape. And then it's taking that light, it's not losing any light, it's incredible. Focusing all that light in a fiber optic tube, which travels down underground, which then hits a prism and gets dispersed onto the actual plants. So it's physically taking sun's light and traveling, and this tube can turn. That's the cool part. If you know about FiOS, the whole premise behind Verizon FiOS is our cables are underground. That's their big thing. You notice that they try to pride themselves on over not losing a signal level. Because, when we talk about Dish Network in this class, or the other class, I forget which one, but Dish Network, the weather affecting it, or even like something like another cable phone, like Spectrum that runs above ground. Everything for Verizon is on the ground until it gets to your area. And then there's one pole that comes out of the ground, and that pole, all the cables go to your houses in the area. That's physically how it works. So in this section, we're going to talk about that as an application of what we're calling total internal reflection. Because the EM rays that are traveling through the fiber optic cables, they hit at such high angles, that the signal never leaves the cable. And that's why you're getting such a good signal. That's why Verizon FiOS recently came out with gigabit internet, because they're able to get speeds up to that capacity because of their infrastructure. So they put a lot of money into R&D a long time ago to figure out the best way to deliver a signal in a good manner, in a manner that's not like you're getting fuzziness in your TV and stuff. And that's physically what they're using to do this. So we'll talk more about it as we go through it. So let's talk about the math behind it real quick. You guys all saw that eventually, when the angle became critical, the light ray of refraction bent so much that it was bending at 90 degrees. And eventually it would bend back into the water itself. So what we can do is we can say that when the critical angle occurs, right, when the incident angle becomes critical, we can say that the refracted angle becomes 90 degrees. So let's write Snell's law. And let's just go ahead and plug in now. Let's go ahead and plug in what we know. We know that the incident angle is now called critical. So the incident angle just gets a new name. It's now called critical when it hits at the right angle. Just a new name. It's still the incident angle. It's still the angle from the first material. Then what's interesting though is to recognize that the theta r becomes 90 degrees. When theta r is 90 degrees, what's the sine of 90 degrees? Peter? It's 1. So we can put sine of 90 there, which just becomes 1. So it doesn't affect the answer. And my goal here is to determine a formula for the critical angle. How can I get critical angle by itself? How can I get theta c by itself? Tell me what I should do next.
Divide ni over ni.
Good.
And then sine. Then you multiply both sides by sine negative 1.
Very good. So let's take the sine inverse of both sides. So theta critical is the sine inverse of nr over ni. This is the next formula after Snell's law on your formula sheet. You don't have to memorize this. It's right after Snell's law on the formula sheet. But you need to know what this means. Okay, if you just want to use it, you're not going to know what these actual materials are. Ni is the first material. Nr is the second material. That's literally all they are. So if you're in doubt, and you go to do this on the calculator, and it says error. It says error. You know what that means? It means you switch these around. Okay, it means you switch them around. Fun fact, the sine function only goes from 1 to negative 1 in its range. A sine wave looks like this. Therefore, you can never take a sine inverse of a number that is more than 1 or less than negative 1. So whatever you plug in here has to be a decimal or up to 1. or a negative decimal, or down to -1. But if you try to plug in 3, try it right now. Do sine inverse of 3 on the calculator. It's going to say something that causes a problem. You can try any number in sine inverse. If that number is greater than 1, it's not going to work. So if you mix up your NR and NI, it's not going to work.
What do you mean by material, first and second material?
So coming from air, and then the light ray goes into water, air would be the first, water would be the second. For all of these applications for critical angle, it's always going to go from a slow to fast medium. So it's never going to go from air to something else. It's always going to be like from diamond to air, from water to air, from glass to air. You know what I'm saying? Okay, slower to faster is always the idea here. Okay, so again, if you tried something like, let's say hypothetically say that you put 2.4 for diamond up here, and you put 1 for air. You do the sine inverse of 2.4 over 1, you'll get an error. Because you can't go from air, incident air, to diamond and have total internal reflection. It's only from diamond to air that occurs. Okay, so if you ever get an error with a sine inverse, it probably means that your argument, the thing inside, this is called the argument is probably inverted for this type of an application. Okay, in math you'll do this as well, but for this application I'm talking about. Let's do an example of this. Determine the critical angle for light traveling, here we go, from diamond into air. So let's see the angle that causes total or internal reflection for a diamond. Now remember, anything more than this angle will also work. So if I go ahead and look at this, we're going from diamond, and that's 2.42. It's in your table. Okay, it's in your table. I happened to do it like 2 periods ago, so I know the number. Okay, it's 2.42 from your table. And air, we know, is simply 1. Our goal is to find the critical angle. This is just plug and chug. It is so easy. You're literally plugging in every single time. We have NR over NI. And if you forget which way the formula is, just look at your numbers. The smaller number has to go on the top. Okay, give me one more second. This is the sine inverse of 1 over 2. We have examined, so we're in no rush. 1 over 2.42. Check it out. You'll get around 24.4 degrees. Now, let me talk real quick about what this means. I explained earlier about the idea that a diamond seems to sparkle a lot more than other glasses, right? But we talked about how cubic zirconia is like a knockoff diamond, has kind of the same sparkly effect, because its value is 2.2. Somebody check it out, please, real quick for me. Plug in a 2.2 here instead. Look at the angle difference between diamond and cubic zirconia. What do you got, Em? I see you typing away, or Sarah, either way. What is it? 27? So look at that difference. Not much at all. What this means is this. Any angle that the light trying to escape the diamond hits that's greater than this will not escape. So if the light is exiting the diamond at an angle of 25 degrees, it's not going to escape. It's going to get bent back in. But if it's exiting the diamond at an angle of 16 degrees, it will escape. Anything greater than or equal to the critical angle will automatically cause total internal reflection. This is really interesting because look, there's a lot of numbers above 24 before 90, aren't there? Can't go above 90, by the way. But the majority of the angles, so between 24.4 all the way up to 90, if light hits the surface from diamond to air, at any of those angles from 24.4 to 90, it's not going to leave this diamond. It's going to sparkle, which is why diamonds sparkle so much. Majority of things are exiting at angles greater than this. We're looking at, this is 24 degrees below, and above that, what are we looking at? We're looking at 66 degrees. So there's a lot higher chance that the light gets trapped than it escapes. A lot higher chance that it gets trapped than escapes. And the same goes for cubic zirconia. They try glass. I think glass is 1.5 or 1.3 or something. You're going to do it in your lab anyway, so it's not a big deal. But try these other ones and you'll see how the angles get much bigger. Diamond has the best capability of sparkling because this is such a low number. Now, diamond has other properties like its hardness and other things that make it so much more valuable than this, okay? And the sparkling effect. The hardness of diamond is actually what gives it its value more than anything else. What's interesting, if you look at the next slide, you'll see this, is that you can also create polymers or synthetics that do the same thing that are not diamond. So Fios created their own what are called light pipes. These are called light pipes, thin glass pieces that the angle, look at these angles, guys. I mean, look at this. Here's the normal. Draw a normal in. It's crazy to think about these angles. Look at them. Let me draw one normal. There's the normal for the first one. Look how big that angle is. That's definitely bigger than 24 degrees. It's measured from the normal to the actual incident ray. That's definitely more than 24. And the material that they use to fiber optic cables actually is more refractive than diamond is. But it's not as expensive because it's a polymer, it's a synthetic thing made. So these cables are made in such a way that no rays are escaping. None. Sorry. No rays are physically escaping. EM rays are just going to literally bounce back and forth. And that's what's happening when you go to the carnival. And you guys see these at a carnival or a fair or like a, what do they call festivals, I guess is the word for it. You know, like when you have the rides come in, the Ferris wheel and stuff. This is what you see. This is one of the, like when it was, I did this when I was a kid. This was like one of the prizes you would win. And you squeeze a little thing in the middle and it turns the power source on. And all the light travels through these little light pipes. Yet you don't see any light here. Because none of the light is escaping the light pipes. It's getting bent back in until the end where the light comes out. Which is this light ray coming out at the end only. Nothing is escaping the light pipe. This is how fiber optics physically work. Okay, and this is the concept behind what we're talking about with the farming underground. The light that's focused travels through these things called light pipes or fiber optic cables. And then at the end, there's a diffuser mechanism which causes the light to spread out. And that light actually is affecting a small area of plants or crops. Okay, I want to finish quick. I know we will do examine, I promise. With just the idea of a prism. Okay, a prism simply disperses light. It bends white light. And you guys know that white light is the combination of all those colors. When you see a white surface, all those colors are coming at you. So when I see this as white, I see every color coming at me. So if I held up a prism and had white light behind it, all those colors would actually slowly show up because it would bend the light to cause the light to slow or speed up, and it would separate into its little mini spectrum, its mini range of colors. Okay, and we'll do more with the prism in the next section. I just wanted to at least get to the beginning of this idea. Okay, so this is the homework to take a quick look at, please. I don't think I see you guys tomorrow, is that right? Unfortunately, I don't think I do. Day 3. I think day 3 is the one day I don't see you. So this homework for you guys, I think, is due on Monday. So take a look at Moodle to see